Have you ever wondered if something as fragile as an egg could actually break solid rock if thrown with enough force? While this might sound impossible, the physics behind high-velocity impacts reveals some truly surprising possibilities. When objects collide at extreme speeds, the laws of physics begin to behave in counterintuitive ways that challenge our everyday understanding of strength and fragility. The secret lies in kinetic energy, which increases exponentially with velocity. According to the formula, kinetic energy equals 1/2 mass times velocity squared. This means that even a lightweight egg, when accelerated to extreme speeds, can carry tremendous destructive force. At velocities exceeding 100 meters per second, an ordinary chicken egg transforms from a breakfast ingredient into a potential projectile weapon capable of causing significant damage. Real-world evidence supports this phenomenon through extensive ballistic testing. Military researchers have documented instances where soft materials traveling at hypersonic speeds can penetrate or fracture much harder substances. Water droplets fired from specialized cannons have been observed creating craters in metal surfaces, demonstrating that material hardness becomes less relevant at extreme velocities. The mechanism behind this involves stress wave propagation through crystalline structures. When an egg impacts rock at sufficient velocity, it generates shock waves that travel faster than the rock's ability to redistribute the stress. These waves create localized pressure points that exceed the rock's tensile strength, causing microscopic fractures that can propagate into visible cracks or complete structural failure. NASA's space debris research provides compelling evidence of this principle in action. Tiny paint flecks traveling at orbital velocities of 17,500 miles per hour can chip spacecraft windows and damage sensitive equipment. These microscopic particles, far smaller than an egg, demonstrate how extreme velocity compensates for minimal mass and destructive potential. Laboratory experiments have successfully demonstrated egg versus rock scenarios using specialized pneumatic cannons. Researchers at ballistics laboratories have accelerated eggs to speeds approaching 200 meters per second, achieving sufficient impact force to crack limestone and sandstone samples. The key threshold appears to be approximately 150 meters per second for most common rock types. The egg's internal structure actually enhances its destructive capability at high speeds. Upon impact, the liquid contents create hydraulic pressure waves while the shell fragments act as secondary projectiles. This combination effect multiplies the initial impact force, creating a more complex and destructive interaction than simple solid-to-solid collision. Historical military applications have utilized similar principles in ammunition design. Soft-core bullets and frangible projectiles rely on controlled fragmentation and energy transfer rather than penetrator hardness. These designs demonstrate that strategic material properties can be more effective than simple hardness when properly engineered for specific impact scenarios. The minimum velocity required for an egg to break rock depends on several factors including rock density, porosity, and crystalline structure. Sedimentary rocks like limestone require lower impact velocities than igneous rocks like granite. Calculations suggest that a standard 60-gram egg would need to travel at approximately 120 to 180 meters per second to reliably fracture most common rock specimens. While achieving these velocities with thrown eggs remains practically impossible using human strength alone, the theoretical foundation proves that under the right conditions, fragile materials can indeed break seemingly indestructible ones. This principle continues to influence modern engineering applications from spacecraft shielding design to industrial demolition techniques, proving that in physics, assumptions about strength and weakness often crumble under extreme conditions.
Thank you for watching. Please like and subscribe.